Okay, good morning, everyone. Today we'll look at chapter 5, AC analysis. As I like to say, the good stuff. What we will do here is mostly look at math. Now, when I say the word mostly look at math, it causes apprehension in students. But what I would say is we're going to use, the math is not complicated. It's actually the opposite. We will use complex numbers to actually make the math less complex. Okay. AC analysis requires solving of differential equations. But by using complex numbers, we will be able to reduce these equations into simple circuit analysis problems. So all the analysis techniques that we learned in chapters 1 and 2 will be applied exactly the same way, except the quantities are now complex numbers. That's the only thing. And so if you have not yet taken a look at the complex number worksheet that I've posted on the website, please go ahead and do so. Remember, I pointed this out earlier, I think on the first day of class and also somewhere in the middle. Download that worksheet. You need to learn how to do complex number math on your own calculator devices. You can use online solvers, you can use your devices, you can use MATLAB, whatever you want, but you need to be an expert at doing so on your own devices. Okay. Before I get into AC, I want to cover one slide from chapter 1. This is something that I typically do on the first day of class, but because of the holiday this quarter, I was not able to do so. So let's go ahead and do chapter 1 and look at the slide. Okay. How many of you have heard of this war of currents or the current war? Anyone? Some people have. Okay, there's actually a movie based on the series of events, came out, I think, in 2017 or 2018, starring Nicholas Hoult and Benedict Cumberbatch, I believe. It was not a literal war, but there was some, it was basically a battle between two competing technologies in the late 1800s. This was basically the era where electricity was just discovered and means of generation and distribution was just coming up in the world. So this is something that took place in the US between Edison and Tesla, both well-known personalities. Late 1800s, Edison was already established business person. He had his factories factories running, several projects all at once. He had engineers, researchers, scientists working for him. He was a very powerful person in his day. He was a charmer, and by all accounts, he knew how to charm people into investing money into his company. And as is usually the case, if an employee of a corporation comes up with something new, it belongs to that corporation. So many of the inventions that are attributed to him are basically the work of several hundred researchers. Nikola Tesla was, from what I recall, is a place in Serbia, in modern day Serbia. He was a mathematical genius. He could visualize solutions in his head and do complicated theory in his brain. He was kind of the opposite of Edison. Edison, ironically, would be somebody who would fit in perfectly as learn by doing, because maybe he was not so good at math. I don't know. But what he would do is he would take a problem, and instead of spending time trying to do a theoretical analysis, he would right away get to work trying to actually do stuff. If it didn't work, he would try something else, Whereas Tesla was somebody who would do theoretical calculations and would realize that this approach would not work, so he would not waste his time trying to actually make something practical. Does that make sense? Right? Now, all of this is based on historical anecdotes. We don't know if it's true or not because none of us were alive at the time. But from all historical accounts, this is pretty much how it went down. So Tesla was recruited by Edison or one of his managers to come over from Europe to the US to work for Edison. He, at the time, was already brilliant. He was a big name at the time in Europe for working on inductors, inductive coils, and transformers in a lot to do with the AC generation, AC analysis. Edison at the time had some kind of unsolvable problem, and he put a bounty on it of about $100,000. Nobody could solve it. When Edison came along, he solved it, and he asked for his prize. Story goes that Edison laughed in his face and said that he was just joking. Tesla was Edison's employee, so it was part of his duties as an employee, and not, he was not going to give him that money. Don't know if that's true or not, but again, that's how the story goes. So they had a big falling out, and then Edison and Tesla parted ways shortly thereafter. So Tesla left his employment and went ahead and met with other investors trying to work on AC generation and AC distribution. So from that point on, Edison, who by all accounts was also a first-rate jerk, did all in his power to denigrate Tesla and his work. He actually hired people, and this is well known, he hired anonymous people to capture stray animals and electrocute them on streets, doing street shows to show that AC was very dangerous. And then his own DC power or DC electricity was safe. What, of course, he wouldn't tell people was that the AC electrocution was run at hundreds and thousands of volts, whereas his DC was like very low voltages. So you could have like a light bulb running at like 10, 15, 20 volts, which would work just fine, but it wouldn't do any damage to humans or any other animal. But if hundreds of volts to animals, they for sure would be electrocuted. And think about this, because this was in the early days. Electricity is unknown. The only brush with electricity people know is lightning. Even if people have never seen in person, they are aware of lightning, right? Lightning strikes. And now they're thinking artificial lightning carried over wires, and people actually getting electrocuted and dying during the installation, during like crisscrossing of wires, fires breaking out. This is all, it happens all the time. It even happens in modern day times, right? So at that time, it was completely unknown. People were scared of this. And then if they see somebody on the street showing, hey, AC, this is what AC does to you, don't support AC, people were scared. All came to a big, big confrontation. It was a series of events. Tesla had the backing of George Westinghouse. Westinghouse is a brand that is still in existence today. Edison's company was known as Edison Electric. Through a series of mergers, that company is still in existence today. General Electric. So Edison Electric was a result of a merger of Edison and another corporation at the time, and then through a series of mergers and acquisitions and name changes, it came to be known as General Electric, which General Electric by now on a segue is just, instead of being a manufacturer, is now just a hedge fund company that owns a few businesses. Anyway, so Tesla and Edison, Edison was supporting DC, Tesla was supporting AC. They bid on electrification of the World's Fair in Chicago. Tesla's bid came in about $100,000 cheaper than anyone else. 100,000 more than 100 years ago is a huge amount of money. They won the bid. They were able to successfully electrify the World's Fair, and from that point on, AC just took off. Okay. Edison's engineers and salespeople had a hard time selling DC power and DC generation because it had limitations. It needed special lines, it needed special equipment, it couldn't be transmitted successfully for long distances. Whereas AC has the capability to be transmitted over long distances. Using transformers, you can step up or increase the voltage of AC to tens of thousands of volts, and you send it over long distances. The point of increasing the levels is so that anything transmitted over long distances loses, there's power loss that happens. And so if it's high enough number, the power loss at the other end is not significant. That's the reason. And then when it reaches the destination, you can use transformers again to decrease or step down the voltages. Okay. All of that work was done by several hundred researchers, but Tesla did a lot of the work in bringing it to market in like a usable form. Okay. So transformers primarily attributed to 3 Hungarian researchers, but Tesla had his own inventions of the Tesla coil, wireless charging, electric motor, and evidence of that is all around us in everyday life, right? The electric vehicle company named after Tesla, wireless charging that we use in our devices nowadays. Again, magnetic fields interlocking wirelessly, that is also attributed to Tesla. Tesla actually had an idea at the time of his death. He poured his money into setting up a free power station for everybody, meaning it would be a true wireless power transmitter. Huge coil and just transmitting power, radiating power in the air. So you would not need to plug anything into the wall. You could simply just take your device, leave it here. It would pull in signals, and the coil inside your devices would actually convert it into electricity. So that power station, I think, is somewhere in New York, Staten Island or somewhere. It was still in existence until recently. Now it's like a museum, I think. World's first power station, or one of the earliest power stations, was set up near Niagara Falls. Nice round number was chosen. And then from that point on, electricity was, once they were safely able to install and distribute electricity, it just became the norm. So that, in a nutshell, is, or very, very brief explanation, is the War of Current. The movie came out in 2017, 2018. Check it out when you have some time. Let's see what else. No, that's about it. There's a lot of stories in there. So again, if you're interested, do check it out. So general knowledge question. I think I mentioned this on the first day of class. What is the voltage rating of the power outlet in North America? 120 volts. Could be 110 to 120 volts. The reason for that is when they first set it up, they chose a nice round number, which I stated, right? Nice round number of 100. Built a 10% tolerance in it, 110 volts. And then once the infrastructure and everything was set up, you can't increase it without causing costs of like trillions of dollars. So everything now runs at 110 to 120 volts. The rest of the world came later, and so they set up higher voltage. Simple reason, electrical power is a product of voltage or current, V times I. If you want power to be transmitted and you want to increase the power, you either increase the voltage or you increase the current. Of the two, it's easier to increase the voltage. Also more efficient, because power is also I squared times R. Long distance transmission lines, even though the resistance would be very, very small, long distances mean hundreds of miles long. Resistance is rho L over A, directly proportional to the length of that wire. So the longer the wire, the higher the resistance. If it's a short wire, 6 feet, 25 feet, 100 feet, not much resistance. Hundreds of miles, there is enough resistance that power losses would occur. If your current increases, power losses are square of the current. So more efficient to increase and easier to increase the voltage rather than to increase the current. So the rest of the world stepped up their voltages from 110 to 220 volts. So most of Europe, most of Asia uses 220 to 240 volts. North America uses 110 to 120 volts. Now we go chapter 5. The title for the chapter is Sinusoidal Analysis. Okay, sinusoidal analysis. And I'll explain what it actually means. So what you're going to study in this chapter is basically the work of AC, the effect of AC sources on our components, resistors, resistors, inductors, and capacitors. The components don't change. The components are the same. The only thing that changes is the source. The source, instead of being DC, is now AC. Could be AC voltage, could be AC current. So when we say AC circuits, we are simply referring to the same circuit, but a different source. That's all. So we look at how we can mathematically model the relationships between the voltage and the current for these components. Here are graphical illustrations of the typical AC voltages. You don't have to draw any of these out. On the x-axis, on these graphical representations, we always have time. Okay. If you plot the value of a DC voltage or current as a function of time, you would expect a flat line. This could be voltage or current or power. This is DC, right? Flat line, constant, doesn't change. Take a 1.5 volt battery. It's going to show you 1.5 volts right now, 5 seconds later, 5 days later, 5 months later. Well, within reason, but constant with respect to time. AC, if you plot it out, is any waveform that changes its value. It doesn't really matter the shape of the waveform, doesn't really matter the value of the waveform. If the value changes constantly with respect to time, it's AC. The reason it's called alternating is because of the sinusoidal waveforms that alternated between a north and a south pole, positive and negative. So based on the shape of the waveform of the value, we have triangular, we have square, we have rectangular, and we have ramp, sawtooth, many different kinds, different purposes, different applications. Okay. The only waveform that we study is the sinusoidal waveform. And it's known as sinusoidal waveform. It can represent it mathematically as a sine or cosine function. Okay, sine or cosine function. We'll look at this waveform in detail. We'll look at the equation that is used to describe this waveform and all the individual quantities, every single slide. Quick note about how it's generated. You have a coil, inductive coil inside a magnetic field. The magnetic field has a north and a south pole. So this inductive coil rotates inside a magnetic field, causes the motion of electrons, and the motion of electrons in the electric circuit, because it's going to a north pole and a south pole, north pole and a south pole, and a continuous circular motion, generates a sinusoidal shaped waveform. You can check out YouTube. There are several videos, and there are really cool videos that actually show you how a circular motion of a generator is transformed into a electric current. Okay, but the reason for the positive and negative is because it's rotating between a north pole and a south pole of a magnetic field constantly. So positive peak is associated with the north pole, negative peak with the south pole. So it alternates, hence the name alternating current, AC. So this is the mathematical representation of a waveform. When I say waveform, I'm referring to the graphical representation, right? But in electrical engineering, we use this synonymously with function, with signal, and it could mean either voltage or current or any quantity. So if you hear me say the words waveform or function or signal, be aware that I could be referring to that voltage or to that current. So this form of the waveform is V of t is Vm cos of omega t plus theta. We will look at each one of these quantities individually. Okay, individually. This can describe either current or power, voltage, current, or power, V of t or I of t or even P of t. Okay, mostly we'll look at voltage and current, V of t and I of t. The voltage value as a function of time is given by this expression. The first quantity is Vm. It is also referred to as Vp. The subscript m stands for magnitude or the amplitude or the peak value of the waveform. This can also describe Im or Ip. And it's simply giving you the value on the y-axis. It's the value of the waveform on the y-axis. X-axis is always time. Okay, x-axis is always time in seconds. Y-axis could be voltage, could be current, but it's giving you the value of that quantity on the y-axis. the function or the expression or the equation as a whole is describing that quantity, meaning you could plug in values of time t and you could obtain the value of that function at that given point in time. That's all it is. There is a reason why those quantities are kept separate. Okay. So again, as I said, Vm, the first quantity, is the magnitude or the peak value on the y-axis. Second is omega, lowercase Greek letter omega, the angular frequency or angular velocity in radians per second. And then phase, theta, again, Greek letter theta in degrees. We can convert those degrees into radians and combine it, but there is a reason we keep it separate. Because, again, as we said, complex math, we're going to represent this time varying function as a vector. For that, we would need that phase angle. So we keep it separate. Okay. All three quantities have three different units. If it's V of t, then Vm has volts, omega is radians per second, and then theta is in degrees. But that equation is describing voltage as a function of time. So the entire mathematical expression has units of volts. Unit of volts. Okay. And then we'll look at those three quantities in detail. Then you can ask your questions. All right. One thing also you should be aware of is the identity sine x is cos of x minus 90. That will come up later. So magnitude or amplitude or peak value. Now our system and our book uses magnitude, the subscript m. But most books and most systems will use the subscript P for peak. You should be aware and recognize that they are the exact same thing. So if somebody like a peer student or a friend from a different class talks about peak values, then they're talking about the magnitude, Vm or Im. Okay. It simply states or gives the quantity value on the y-axis. So here you have waveform 1, 2, and 3. The first value, of course, is 0.5, 1, and 2. So the value of the quantity on the y-axis is given by that first term. Important to note, it's only describing one peak, not both. Vm or Vp is describing one peak, not both. If you wish to describe both peaks, again, because it's sinusoidal, the assumption it's symmetrical around the x-axis, you would use the term P dash P, which is 2 times Vm or 2 times Vp. And P dash P stands for peak to peak values. Okay, peak to peak. Any questions about the peak values or the amplitude? Okay, let's go into here. Yes. Yes. Peak to peak means positive and negative together, and its assumption is symmetrical around the x-axis, and so you just take twice the value of Vm or Vp. Okay. So a sinusoidal waveform will start at 0, go to a positive number, come back to 0, then start at 0, go to a negative number, negative peak, and come back to 0. When it does this, we say it has completed one full cycle. One full cycle. The positive peak is known as the positive half cycle. And the negative peak is the negative half cycle. So it goes to a positive number, positive peak, goes to negative, comes back to 0. One full cycle. That one full cycle is mathematically represented by uppercase T. Typically, it's in seconds. It's known as the time period of the waveform. Time period of the waveform. If you take the inverse of the time period, you get what is known as the frequency of the waveform. Lowercase f, they're reciprocals of each other. Frequency f is 1 over t. Unit is named after the German physicist Hertz. Acronym is Hz, Hertz. Hertz. In simple terms, it also is the number of cycles that a waveform completes in 1 second. So frequency f is the number of cycles in 1 second. So you go up, go down, back up to 0. 1 cycle, number of cycles in 1 second is the frequency of the waveform. So back to the general knowledge question, what is the frequency of North American power outlet? 60 Hertz. If you look at any adapter for any device that you use or any appliance that you use, it will have a voltage rating and a frequency rating. It's very tiny letters, but it's there. Input will state. Nowadays, most chargers and most adapters can be used worldwide. So the input will state 100-240 volts, comma 50-60 Hertz. Meaning you could plug that adapter anywhere in the world and it would work just fine. No need for any electrical conversion. You might have to do a physical conversion because physical designs are different in different parts of the world, but you would not have to do any electrical conversion. So every time you plug in an adapter, you always have to be aware whether it will work. So 60 Hertz, that means the power outlet goes from 0 to positive to negative to 0 60 times in 1 second. That fast. Right? Now, if you were Dr. Strange and had the power to slow down time, you could stick your finger in the wall and you could feel the voltage go up, go down, go up, go down. But thankfully, none of you are Dr. Strange or have the power to slow down time. So don't stick your finger in the wall. It's not a pleasant sensation. 60 Hertz might seem like a very high frequency, but it's actually a very, very, very low frequency. Okay. Normal human hearing range is between 20 Hertz to 20 kilohertz. Most people like me can't even hear anything below 100 Hertz, perhaps. Okay. 100 Hertz is a low frequency. You need really big speakers, specialized amplifiers known as subwoofers to actually even reproduce those kind of frequencies. The lower the frequency, the larger the speaker size that you need. Higher range goes thousands of Hertz, right? Thousands of Hertz means thousands of times in 1 second. But again, that's not even considered as a high frequency. normal operating radio stations like AM and FM, AM radio stations and FM radio stations, the name of the radio station actually has a technical meaning. It is the broadcasting frequency of that radio station. So 680 AM stands for 680 kilohertz of the frequency of the broadcast. 101.7 FM is 101.7 megahertz of frequency of that broadcast station. So kilohertz, 1000, megahertz, 10⁶. Wireless routers, gigahertz, 10⁹. Microwaves, cordless phones, all 2.4 gigahertz or 5 gigahertz. So really high frequencies. So the wireless routers that we use, mobile phone signals that we use, they all run in the megahertz and gigahertz range, right? Very, very high frequencies. So 60 hertz is basically nothing, very, very low. And finally, we have phase. The reason we keep phase separate is because we need to describe a vector, complex numbers. All right, before I do that, here, this is time t. This is time t equals 0, right? Simply our reference point. And we have waveforms 1, 2, and 3. These are not 0.5, these are just 1. Okay, this one. Amplitude's the same, even the frequency is the same. The difference in this is the phase. And phase can be explained like this. These are positive values, positive numbers, right? T is +1, +2, +3, +4 on the right. And on the left, you have negative numbers. -1, -2, -3, -4 on the left. But because it's time on the x-axis, what do those positive numbers actually mean? If times t equal to 0, +1, +2, +3 means it's the future. Time is yet to come. So this is the future, and negative numbers is the past. Right? -1, -2, -3, meaning time is already gone by. If you're analyzing a time t equal to 0, -1 represents the time that's already gone by in the past, right? We saw that in chapter 4 analysis. Time t equal to 0, so we just flipped. We analyze for time t greater than 0, meaning what's going to happen in the future. But what happened in the past is time t less than 0. Same thing. So the phase is describing the moment in time when the value or the waveform crosses the x-axis, meaning the value of the waveform goes to 0. So if you look at waveform number 2, waveform number 2 crosses the x-axis at time t equals 0. So the phase of that waveform is 0. Right here. 0. Okay, let me write it as +0. Waveform in blue compared to the waveform in black has already crossed the x-axis prior to time t equal to 0. It's in the past. The bus is already gone. Just take a few seconds and think about it. It's in the past. The blue waveform has already passed by. And so that is represented with a positive phase number, +5. Does that make sense? Any questions? Similarly, if you look at the waveform in red, waveform number 1, it is behind. It crosses the x-axis after time t equal to 0. So it is yet to arrive. It's yet to arrive. And so that is represented by a negative phase. And again, the reason we keep it separate is because we wish to describe it as a vector. Okay. Positive phase is noted by the word leads, negative by the word lags. It's similar to the concept of ahead and behind. If you have two people walking down the street, person one is ahead of person two. At the same time, we can describe person two as behind person one. So if you have two waveforms with a phase shift, we can say waveform one is leading waveform two, or waveform two is lagging waveform one. Make sense? Kind of like a crude analogy, but in my head, it makes sense. Leading and lagging is ahead or behind. Okay. All right. So now let me ask you this. Sinusoidal waveform, symmetrical around the x-axis. What is the average value of that waveform? Elementary school math, it's 0. I've been saying it a lot. Elementary school math in my labs, in my lecture classes. But it's 0, right? You get positive half cycle, you get negative half cycle. Both are symmetrical. Average value is 0. Yet energy is still being transferred. So how do we mathematically represent that equation? Think of it in this terms. If you have all the negative peaks, flip it on the x-axis. Okay. If there are mountains of dirt and you flatten them out, what value would you get? It would be kind of an equivalent DC value that would produce the same energy. Okay. You take the negative and the positive values, there are mountains of dirt, you flatten them out, you get a new value, right? That value came about like this. So we couldn't take the average of the waveform. So the early researchers, they decided, instead of taking the average at first, what we will do is we will take the square of that waveform first, then we will take the average. Okay, we won't take the average of the waveform, but we'll take the average of the square of the waveform. And now that we have the average, because we took the square as the first step, at the end, we will now take a square root. So they came up with a term known as root mean square. It literally is the square root of the average of the square of that waveform. And mean is, of course, just another synonym average. This is better known by its acronym RMS, RMS value. Again, it literally is just the root of the mean of the square of the waveform. As a first step, we have the waveform, let's say V of t. What do? We take the square right there, right? We take the square first, then we sum it up. Summation, integration is nothing but summation. You have individual slices, d of t, dt. You add up all the slices, meaning integrate from 0 to t over one time period. Then you take the average, divide by t, 1 over t. And then because we took a square as the first step, at the end as the last step, we take the square root, which is right here. So RMS value is nothing but, again, it's the root of the mean of the square of the waveform, RMS. It literally describes the average value of that waveform. So if we were trying to determine the average power in a resistor, let's say, or DC voltage or DC current, we would simply do V squared over R or I squared times R. The equations still remain the same, except for an AC waveform, we apply an RMS value. We cannot do a time value because a time value as a function of time, it changes. Any given point in time is different. We can find P, power as a function of time, but we can't find the average power being transmitted to a resistor. So to do that, we use the RMS value. So same equation, but it's now the RMS value of the AC waveform. So V RMS square over R, or I RMS square times R. The same equations work. Okay. Make sense? Now, for sinusoids and sinusoidal waveforms only, there is a derivation. Again, it's a mathematical representation, right? You plug in sine x and cos x in that equation, and you solve it. We don't do that for non-E major classes. If you're interested, stop by my office. We can go over it together. I can show you the book. And it comes out, the relationship between the two is given by this expression. RMS values are found from the magnitudes divided by √2. So mathematically, VRMS is VM over √2, or VM is √2 times VRMS. Think back to the sketch I made. Mountains of dirt flattened out. The peak values of those mountains will always be higher than the average value. So magnitude values will always be higher than the RMS values, always. And you can see that in the mathematical expression, right? √2 is 1.41, almost 1.5 times the RMS values. So peak values will always be higher than RMS values. So then the question I would ask is, are power outlets and all the voltages that we refer to in real life, are they RMS or are they peak? Here's a hint. RMS value is describing one value for all instants in time, one single value. Whereas peak values are only describing one value at one point in time. So if you're describing a peak value, you need an additional descriptor with it, which we don't. So again, 120 volts, is it peak or is it RMS? RMS, because it's describing an RMS. So unless explicitly stated otherwise, all values are always RMS. All measurement meters, all analysis is always RMS values. It's never peak. If it's peak, it will be stated. Okay, it'll be stated as peak value or magnitude. Otherwise, it's always RMS. So why sinusoidal? Well, sinusoidal voltages are easy to generate, remember, or easier to generate, right? Decades of research has gone behind it. As I said, right? Mechanical movement due to hydropower, due to water, or wind power, wind turbines. That mechanical movement converts that electric coil, sorry, not converts, causes the inductive coil to move inside that magnetic field, which causes electricity to be generated. This electricity can be transmitted over long distance with ease because it is easier to increase the levels of AC voltages by simply using transformers. Optimus Prime is not coming, but we have a transformer that is two inductances connected around a magnetic core. It's easy to increase the level, and then at the end, distribution, it can be easy to decrease it. If you have noticed around a residential street, you have these light poles all going down a residential street. Every once in a while, the light pole would have a metallic cylinder. That metallic cylinder is not from Cybertron. It's from PG&E that distributes, that takes the high voltage lines coming in and distributes different wires going into each house. So next time you're going down a residential street, you can take a look. You might see a single connection with a transformer and different wires going into each house. Typical high voltage transformers, there's one actually, say, if you go by the E building right before you hit Dexter Lawn, there is a wooden fence. I think it states high voltage, do not enter or do not touch. That has a high voltage distribution transformer inside it. Okay. So again, it's easy to generate, it's easy to handle, and mathematically, we have to do derivation and integration. Sin x and cos x is the exact same thing. Derivation and integration is also sinusoidal. Sin x is cos x is sin x, right? But I don't know about you, and again, I've stated this before, solving differential equations is not my idea of a good time. I'd rather not do so. Some people enjoy it. What we are going to do is we will represent AC voltages and currents and the components using complex numbers. So here's where we introduce the terms phasors and impedances. These are not the phasors from Star Trek. They're not going to stun or kill you, but they will scramble your brains occasionally. We'll take the sources, sinusoidal sources, and mathematically represent it using complex number. The sources are represented as phasors. Inductors and capacitors are represented as complex number, using complex numbers as impedances. Okay. Now, resistors are not mentioned here because resistors behave the same way for AC as well as the same way that they do for DC. No change, no difference. So there is no complex impedance for a resistor. But inductors and capacitors are energy storage devices. When you apply positive voltage or current to the capacitor or inductor, the energy flows in. When you reverse it, energy flows out. And in AC, it's constantly changing, positive, negative, positive, negative. So for an inductor capacitor, the energy is constantly flowing in and out, depending on how fast the waveform is switching. And so the opposition to that change is represented as impedance. That is what we'll look for. We'll introduce the phasor before I end class for today. So here's a time domain waveform given by V of t, Vm sine or cos of omega t plus or minus theta. The phasor is a rotating vector in the complex plane. Complex plane means we have a real axis on the x and imaginary on the y. Okay. The phasor representation is the vector that is rotating in the complex plane counterclockwise, but it is a snapshot of a single point in time. It's a single instant in time. Okay. It's a single instant in time. It's a vector. It only needs two things to describe itself: magnitude and direction. We need the length of the vector and the phase angle, or the angle it makes with the real axis. That angle is obtained from the phase in degrees. And this is the reason why we keep the phase shift of the waveform separate. That's why we keep it separate in degrees. We do not change it into radians and combine it with omega. This is the reason why. If you have a waveform given in Vm cos of omega t, you only need two things: Vm and phase angle theta. That's it. You can directly write the phasor from the time varying waveform. There is no frequency information in a phasor. It's a rotating vector, but it's a single snapshot. It's a single snapshot of one instant in time. It's a moment in time where it crosses time t equal to 0. Okay. So a phasor can be represented as Vm with the angle theta. The projection of this vector, this is Vm or V peak. The projection of this vector on the y-axis and the x-axis, the real and imaginary axis, gives you the rectangular coordinates. So you can change this to A plus JB. J in electrical engineering is used to represent the imaginary number I, because I is reserved for current. So from here on out, from chapters 5, 6, and 5.5, complex number math, you will use this form. Again, if you have not yet looked at that sheet, download that complex number sheet and do work out those problems. You need to be experts at using your own devices. This is not just for electrical engineering. It's for all engineering fields. Okay. Get started on the homework that is due. I think it's due tomorrow. It's due on Friday, but if it's not covered enough topic here, then I will extend it perhaps, but get started on it as soon as possible. Okay. So we'll end class here and I will see you all on Friday.